Hurwitz and his colleagues decided to examine oxygen isotopes because planets and moons have a distinct oxygen fingerprint that records the exact environmental conditions in which they were born. The paper is published today in Science. Earlier studies found that the proportions of the different oxygen isotopes in Earth and the Moon as averaged over their entire bulk were essentially identical. For the new study, the researchers used an extremely precise laser-based method to measure oxygen isotopes in a range of Earth rocks, meteorites and 3 lunar samples gathered by the Apollo astronauts. They found 12 parts per million more oxygen-17 in the Moon rocks as opposed to the Earth rocks. It's a tiny difference, that's why it hasn't been seen before, says Hurwitz. He suggests that the body that triggered the moon-forming impact, which some scientists call Theia, may have been chemically similar to a class of meteorites called enstatite-chondrites. Those are similar enough to Earth, at least in terms of oxygen, that Theia wouldn't have left a major imprint in the Moon's chemistry, Hurwitz says. Collision debates. Some scientists are not impressed. According to Robert Clayton, a professor emeritus at the University of Chicago in Illinois who pioneered the use of oxygen isotopes in cosmochemistry, the authors may have done little more than find a more precise method of measurement. I don't see anything new in this paper, they've just repackaged the error bars, says Clayton. The observed difference is simply not large enough to say anything significant about the Moon's formation, he says. A minor chemical difference between Earth and Moon rocks could have big implications for theories about how the Moon was born. Moon rocks contain a tiny bit more of the rare isotope oxygen-17 than do the rocks on Earth, say geochemists who measured oxygen using very precise methods. It changes the nature of the debate, says Robin Canup, a planetary scientist at the Southwest Research Institute in Boulder, Colorado, who was not involved in the study. If the difference between Earth and the Moon is a small amount as opposed to 0, we need to know that. Most researchers think that the Moon formed in the very early days of the Solar System, 4.5 billion years ago, when a large protoplanet smashed into the embryonic Earth. Debris from the collision mingled together and then settled into orbit around the Earth, where it coalesced into the Moon. If that were the case, however, scientists would expect to see more of the remains of the original impactor in the Moon. The chemistry of Moon rocks would be different from that of Earth rocks. The big question was always, why do we not see this difference? Why are Earth and the Moon so similar? Says Daniel Hurwitz, an isotope geochemist at the University of Cologne in Germany and a member of the study team. The giant impact is a nice theory that explains a lot of things, but there was this problem.